Hi everyone, this is the notes for 6.1, which is about polygons. So this should be your pink foldable that you guys got a couple classes ago. Okay, so polygons are, poly means many and gons means sides. So the definition of polygons is many sides. And we talked about that before, I think in chapter 2 a little bit, I mentioned it. So polygons are made of segments. So their sides are all segments. So that means that the sides are always straight and they're never curved. And their endpoints of those segments connect at vertices, which we've talked about before. So a vertex can connect only two sides. And a line that connects non-adjacent vertices is called a diagonal. So vertices that aren't touching, a line that connects them would be a diagonal. So if you can see through the picture, from there to there, and that hexagon that's printed on the other side, that would be a diagonal. So if we extend one side, it makes an exterior angle, which we've talked about what exterior angles of triangles were. So that would look something like this. This is our exterior angle. And then the one that's on the inside here is the interior. And the diagonal would be any line that connects non-adjacent vertices. So those are all diagonals. So there's multiple diagonals in a six-sided figure. But we'll talk more about that in a few minutes. So the word convex means a polygon where all of the diagonals are inside the polygon. So that means it doesn't cave into itself. Whereas a concave polygon has diagonals that could be outside the polygon, so it can connect vertices outside. So that means that it makes little caves or insets. Okay, so let's draw some examples of those in our boxes. So a polygon has to have sides that are segments, so they're straight, and it has to be a closed shape. So what would be some examples of a polygon? Well, a square or a four-sided figure would be one example. I want you to come up with at least two more and draw their pictures in there. So any amount of sides would be a polygon. We could even do crazy things as long as their sides are straight. Okay, so if those are polygons, what would be not a polygon? Good. Anything with curved sides, so like a circle or half a circle or an oval, those would not be polygons. Or anything that doesn't close, so if there's an open space. Also, something like that where the sides overlap, that wouldn't be a polygon either. So we talked about convex and concave up there. So convex polygons are polygons that have no caves, so they don't go in. So I drew two of them up here. So the square and the triangle I drew would be a convex polygon. So anything that doesn't have a part that goes in. So those would be convex. Whereas concave is something like this where it goes in and makes a little space inside. And that's because you can connect the diagonal right there with those two vertices. So anything that has that space inside. Or like a star. So those, it's a really ugly star. So those are concave, where they go inside and make little caves. So for the formulas at the bottom, these are giving a lot of different things. We have a lot of formulas. So the first one tells us the angle sum. So all of the angles that are inside a polygon. And that's 180 times n minus 2. And n is the number of sides. So if we're trying to find the measure of one angle inside a regular polygon, so it has to have all equal sides and angles, we do the 180 times n minus 2, but we divide that answer by n, the number of sides. So the exterior angle theorem says that if we have all the exterior angles, they're always, no matter how many sides, going to add up to be 360. And if we want to find the value of just one of those exterior angles in a regular polygon, it would be 360 divided by n, since we have n sides and all of those angles equal 360. And then to find the number of diagonals in a polygon, we do n times n minus 3 divided by 2. So I know we just learned quite a few new formulas. For the inside part, you're going to have some scratch paper to fill in the awesome chart that we made. Okay, so we're going to do one or two together and name a few, and then you're going to have to go and fill in the rest by yourself. So let's try to name them first, and then we'll go back and fill in the spots on the inside. So our first one has 3 sides, and we know that that's called a triangle. If we have 4 sides, I know that looks like a square because the sides and angles are congruent, but we're going to give it its general name, which is a quadrilateral. So quadrilateral has 4 sides. A shape with 5 sides, it's called a pentagon. 6 sides is a hexagon. If you think you know the rest, go ahead and pause and try to fill them on your own, and when you come back, I will show you the rest of the answers. So 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. And 10 sides is a decagon. The names get really crazy the more and more sides they have. I can't even pronounce them, but I have a list if you guys want to know some of the crazy names. When they have like 40 and 50 and 60 sides, I can show you in class. Okay, so let's take a look at the different pieces that we're going to have to fill in for each. So for our triangle, the first blank is the interior angle sum. So what that means is if we add all 3 angles together, what does it equal? So we can use that formula on the front, but we already know the interior angle for a triangle because we worked with that for quite a few chapters. So all the angles inside a triangle add to equal 180. So if we have a regular triangle, what is the value of the interior angles? Good, that's if it's equiangular. They would all be 60. So if this angle on the inside is 60, what's this angle on the outside? Very good, 120. So if we looked at the formulas on the front, we could find all those values by using the formula. For instance, this one on the outside is 360 divided by n. So 360 divided by 3 is where we get that 120 from. Okay, so our last one is our number of diagonals. So I'm going to show you how to use the formula with this one, but if you think about it, connecting our non-adjacent vertices, all of the vertices are adjacent, so it can't be done. But let's try the formula anyways to see what happens. So the formula says n minus 3 times n times n minus 3 over 2. So n is 3 because we have 3 sides. So that would mean we'd have 3 times 3 minus 3 over 2. So since that equals 0, that's why there's no diagonals. Or that's kind of where the formula is built. That's not why there's no diagonals. So there's no diagonals in a triangle. Okay, so let's go over to our quadrilateral. And I know we've talked about the interior angle sum of a quadrilateral, but we're going to do this one with a formula so you guys can see how the formula works. So for the interior angle sum formula, that is 180 times n minus 2. So n is the number of sides, so we would have 180 times 4 minus 2, which is 180 times 2, which gives us 360. So the interior angles of a quadrilateral always add together to equal 360, which we've talked about before. Okay, so let's find the number of diagonals. So that formula was n times n minus 3 over 2. So our value for n is 4. So we'd have 4 times 4 minus 3 over 2. Do parentheses first. So 4 times 1 over 2. 4 times 1 is 4. So that means that there's 2 diagonals in a quadrilateral. And if we wanted to sketch those in so you can see what they would look like, we go from corner to corner. So those would be your diagonals. So those are the only non-adjacent vertices you can connect. So that's why there's 2. Okay, so if our shape is regular and we want to find each angle in a regular polygon, we would do 180 times n minus 2 over n. Well, we already simplified that top formula that was up here, so I'm just going to plug that value in. So 360 over 4 equals 90. So that means that the measure of each interior angle of a regular quadrilateral is 90. So these two angles are supplementary. So that means that the outside one would be 90. But remember, the other way is to do 360 divided by the number of sides. So that's another way to get that 90. One way to get the inside one is to find the outside one first and then subtract from 180, because this formula out here is easier, 360 divided by n, than this formula right here. Okay, so go ahead and pause and try to find the rest of them up to the decagon. I'll work through one more if you're kind of confused and don't know what to do for this one. If you're good, then pause and do the other ones. Okay, so to find our interior angle, our formula was 180 times n minus 2. And for our pentagon, our n is 5. So we'd have 180 times 3, which is 540. So that means that all 5 of those angles added together is equal to 540. And if we wanted to find out what just one of those angles is, so each interior angle, we would take that value and divide by the number of sides we have. So 540 divided by 5, which if we divide that out, we get 108. So that means each interior angle of a regular pentagon is 108. To find the exterior angle, we can subtract from 180 or 360 divided by the number of sides. So we get 72. So that exterior angle when the polygon's regular is 72. So our last one is our number of diagonals. So that formula was n times n minus 3 over 2. N is 5, so we'd have 5 times 5 minus 3 over 2. So 5 times 2 over 2. One way to do this would just be to cross out the common factor, so we would just get 5. Another way would be 5 times 2 is 10, 10 divided by 2 is 5. So there's 5 diagonals in our pentagon. Okay, so I would like you to pause, and when you come back, I will show you the answers. I want you to try to see if you can find the patterns. There's patterns for the diagonal, there's patterns for the interior, exterior angles. They all go up in a pattern. So pause and find for hexagon, heptagon, octagon, nonagon, and decagon. And when you come back, I will show you what those values are. Okay, so you can go ahead and copy those down or check your answers and make sure we're right. I don't know if you've caught the pattern for your diagonals, but we have 0, 2, 5, 9, 14, 20, 27, and 35. Those were our number of diagonals. Do you see the pattern? What happens each time? I'm not going to tell you the answer. I want you to tell me in class tomorrow. Okay, so what's the pattern for the diagonal numbers? Okay, so if you haven't written down all those answers, pause. If you're not sure where I got any of those numbers, make sure you write it down and we can talk about it in class tomorrow. Okay, so let's take a look now at our values at the bottom, or our examples at the bottom, I mean. Okay, so we have several different types of problems here. So our first one, we got this crazy shape and it has 1, 2, 3, 4, 5 sides, so it's a pentagon. Is it a regular pentagon? Good, it's not a regular pentagon because all the sides are different. So we need to find the value of x and those represent the angles. So if we look up at our chart up at the top, we know that the interior angle sum of a pentagon is 540. So that means that all of these pieces add together to equal 40. So one way to write this equation without writing all of those out is to add those numbers together first to make it a little bit simpler. So I have this angle x plus this one, x plus 26, and then I went ahead and added those three numbers so I wouldn't have to write them all down. You could have added 26 with that and added all the numbers and then added the x's. I just was trying to save some steps. So we equal that to the sum of the interior angles of our pentagon. So then from there we can just solve our equation. So combine like terms and then do inverse operations. Okay, so I'm not going to do all that math for you. So go ahead and pause and try it. Okay, so we should have got x equals 83. Make sure you're showing your work. When I'm checking your notes, I'm looking that you wrote down everything. Okay, so let's take a look at the next one. So for this one, they give us some exterior angles, but then some interior angles. So what we need to do first, if we're going to try to find those values of x, is find all of those interior angles. So remember that the exterior and the interior are supplementary, so we can subtract from 180 to find that. So 180 minus 50 is 130. 180 minus 37 is 143. 180 minus 42 is 138. So now that we have all of the insides, we can do what we did last time and add all those together. Do we have a pentagon again? Good. This time we have a hexagon. So a hexagon add together to equal 720. So we're going to add all of those pieces and equal to 720. So if we add our x, 7x plus 3x plus 5x is 15x. And if we take our numbers 40 plus 130 plus 143 plus 138 minus 1, we get 450. So go ahead and show your work. Pause. So you should end up with x equal 18. So make sure you show your work. So the next problem is completely different because this time they give us our exterior angles instead of the interior angles. So we're not going to try to figure out what the sum of the interior angles of a pentagon is. We're going to look at those exterior angles. So remember on the front we said that all of the exterior angles always add together to equal 360. So that means that no matter how many exterior angles you have, they all add to equal 360. So we're going to set all 5 of those exterior angles equal to 360. And you can deal with the shortcut that we did on the last one and add your x's first and add your numbers and just write that part down. Or you could write out all of that added together equals 360. So if we add our x's, we get 11x. And our just plain numbers is 30. And then we can solve for x. So I'm going to show you the next problem. So this one is kind of similar to what we did over here, except they want our final answer to be the exterior angles. So we'd have to find what the interior angles are first, and then we know that those are supplementary. So we got a 90 over here and a 90 over here, but they're not regular, so that means they're not all 90.
Mrs. Jones, to the front office, please.
So this is a hexagon.
To the front office.
This is a hexagon, so a hexagon is equal to 720. So I'm just going to put a variable here so we can write our equation to be able to solve for that x. So we have 4 of those angles that are the same, so I put 4y. And then we have 2 that are 90. So when I solve this equation, I'll get the value of y, and then I can go ahead back and solve for the value of x. So make sure you finish solving that. So the last example is similar to what we just did. They're asking for kind of the exterior angle, and then they showed us that we have 2 shapes. So I know they didn't tell us that these were regular, but we're making that assumption because they didn't give us anything else. So when we have the square, we know that that means 90. And this is a hexagon, so the interior angle of a hexagon is 120. So how would you figure out x? Okay, so I want you to make sure you solve all those problems, have this all figured out, solved, and then done, and make sure you write down any questions, and we'll go over them next class. Werner out.